In the previous video, we are discussing about the power series, and the power series turned out to give you in the form of the series n equal to 0 to infinity of Cn x minus a to the n. And I told you that you have x equal to a, and a here is called the center of the series. And you have the term Cn here. Okay, and you have the term Cn here, which is called the coefficient. And we're gonna be able to, from the center that you can see here, so you have the center at A, you'll be able to find the thing that called the radius of convergence. The radius of convergence is going to be the distance here that is going to give you the radius from the center, and you're going to have the thing that called the interval of convergence. So it's going to be this interval that is called the interval of convergence. So we're gonna find the radius of convergence and the interval of convergence of the following series. So you see that this one you have you have the series x minus 2 to the n and 4 n to the third minus n square. So you see that this guy cannot be n equal to 0 because you see when n equal to 0, this guy turned out to be disappear. So this one we avoid it by just letting the series begin at 1. However, the concept for the radius of conversion and the interval of conversion turned out to be exactly the same. Okay, so for this one, you're gonna first identify the center. So you see that this one, you have the center at a equal to 2. Okay, so you have the center at a equal to 2. So we need to identify the radius of conversion. So we have a equal to 2 for the center, and we like to determine the radius of convergence. So we would like to know the interval of conversion. So for this one, you see that the way to determine the radius of convergence will be using the ratio test. So you're gonna find, so this one will be your UNX. Okay, and you're gonna find limit and go to infinity of un plus 1x over unx. And for this one, you're gonna compute limit n go to infinity. Okay, and you're gonna have x minus 2 to the n plus 1 over 4 n plus 1 to the third minus n plus 1 square. Let me move this one up a little bit. Okay, so this one is un plus 1x, and you have everything over unx, which is x minus 2 to the n over 4n cubed minus n squared. And you see that you must put absolute value like this also. And this one will be given in the way that, so you're gonna get 4n cubed minus n squared. Okay, and on the bottom, so you would have 4n cubed plus the term that I don't care. I'm gonna have the highest one turn out to be 4n to the third. I don't care about the other term. And you're gonna have absolute value of x minus 2. Okay, so let me get rid of this one and this one. So the thing that I would have left is going to be just absolute value of x minus 2. Okay, and so when you take limit n go to infinity, this number turned out to be 1. Okay, so this number turned out to be 1 because you have 4 over 4. Okay, so it's going to turn out to be 1. So this one is equal to absolute value of x minus 2. So you have the limit of absolute un plus 1 over un, and you're going to have x minus 2. And you use the ratio test. By the ratio test, we have the series is convergent. Okay, so by the ratio test, the series is convergent when you have absolute value of x minus 2 that you have here smaller than 1. Okay, so you have absolute x minus 2 is smaller than 1. So the radius of conversion, okay, so the radius of conversion gonna be equal to 1. Okay, so that is gonna be the radius of conversion. So how could we have the interval of conversion? Okay, so you have the radius of conversion is equal to 1. And for finding the interval of convergence, you're gonna plot the center. The center is at a equal to 2. Okay, so you have a equal to 2, and you're gonna have the center turn out to be, so it's gonna be radius turn out to be equal to 1, so it's gonna be 1 step. Okay, so it's going to be 1, and it's going to be 1 here. Okay, and it's going to be 1, 2, 3. Okay, so it's going to be 1 step away from 2, which is the center. And you see that it's going to be conversion in this interval. Okay, so you have, it's turned out to be conversion in this interval, and it's going to be diversion for these two guys. Okay, so it's going to be diversion for this interval, and it's going to be divergent in this interval. However, we don't know about the conversion or diversion at 1 and 3. So when you are dealing with these 2 points at 1 and at 3, okay, so we're gonna have to work on them separately. So we don't know the conversion at 1 and 3 yet. Okay, because the ratio test cannot be concluded when you have the limit equal to 1, which turn out the which turn out to be the case when you have x equal to 1 or x equal to 3, the limit turn out to be equal to 1. So we don't know the conversion at x equal to 1 and x equal to 3 yet. So we're gonna have to work for x equal to 1 and work for x equal to 3 separately. Work on them separately. Okay, so we will work on them separately. So you have when x equal to 1, okay, so when you have x equal to 1, for x equal to 1, you plug in x equal to 1 into the series, okay, x not n, okay, so you're gonna plug in x equal to 1, so it's gonna be, you're gonna have 1 here and n stay the same, so it's gonna be the series so it's gonna turn out to be series n equal to 1 to infinity of negative 1 to the n. So it's going to be 1 minus 2 to the n over 4n to the third minus n squared. Okay, so this one become the series n equal to 1 to infinity of negative 1 to the n, and you have 4n to the third minus n squared. And you see that we shall use the alternating series test in order to test whether this guy is convergent or divergent. Okay, so you may use AST. Okay, so you may use AST. However, we're gonna do x equal to 3. For x equal to 3, you're gonna have series n equal to 1 to infinity of negative 3 minus 2 to the n, and you have 4n to the third minus n squared. And this one turned out to be series n equal to 1 to infinity of 1 over n to the third minus n squared. Okay, so it's going to be 1 over 4n to the third minus n squared. And this one, you will use just limit comparison. Okay, so the limit comparison test. So you have 2 ways to do this too. So when you use limit comparison test, you would like to find limit and go to infinity of this an. Okay, so this one become your an. So it's gonna be 1 over 4n to the third minus n squared, and everything will be, you need bn. So you need bn that you be able to compute this limit. So it's gonna be bn equal to 1/3, 1 over n to the third, okay? And this one become limit n go to infinity of n cubed over 4n cubed minus n squared, and this one you have limit equal to 1/4, which is more than 0, okay? And you have the series n equal to 1 to infinity of 1 over n to the third is convergent. So you're gonna have the conclusion that the series n equal to 1 to infinity of negative 1 to the n of 4n cubed minus n squared is convergent. Okay, so this one is for x equal to 3. So we're gonna conclude this one up here. So this guy is conversion. Okay, so this point you have conversion. And for x equal to 1, you can do this one by AST, or you can just use the theorem. So we're gonna show this one by using the theorem. I'm not gonna show you by using the AST. You can use AST. However, use the theorem will be faster. What is the theorem? The theorem will be you're gonna sin the series of absolute, okay, so absolute negative 1 to the n over 4n cubed minus n squared turn out to be equal to the series n equal to 1 to infinity of 1 over 4n cubed minus n squared. Okay, and this one we know that is conversion. Okay, so this one is by below. Okay, so we can conclude that the series itself negative 1 to the n over 4n cubed minus n squared is also conversion. Okay, so it's going to be is also conversion in this case. So the conclusion for this point is also conversion. So you have conversion for both x equal to 1 and x equal to 3 by using the limit comparison test, and you can use the theorem on absolute conversion. Okay, so you have the absolute conversion. Okay, so it is absolutely conversion. So it means that the series itself is conversion. Okay, this is what we learned last week. Okay, don't forget that we didn't have midterm yet. Okay, so this one you use the fact that when you show that the absolute value turn out to be conversion, the series itself turn out to be also conversion. However, if you have the absolute value turn out to be diversion, you must work on the series on your own, and I would suggest to use the alternating series test. Okay, so we're gonna conclude the interval of conversion. Hence, the interval of conversion is given by, okay, so you basically copy the above picture down. So it's going to be, you have 2 in the middle, you have 1, you have 3, and you have this guy and this guy. Okay, so it's going to turn out to be conversion inside is this interval. Okay, so you have conversion inside this interval. Okay, so it's going to be conversion and it's going to be diversion. Okay, outside. Okay, so this one is going to be the interval of convergence that you use the notation for the closed interval. Okay, like in your high school. The next one, okay, the next one you have negative 2 to the n, x plus 1 to the n over square root n plus 3, okay. So for this one, you're gonna use the ratio test, okay. So you're gonna use the ratio test to find un. First of all, what is un? So this one is unx, and you're gonna find limit n go to infinity of un plus 1x over unx. and you have limit n go to infinity, and you have -2 to the n plus 1, x plus 1 to the n plus 1 over square root n plus 1 plus 3. Okay, so you see that we have 3 places for changing to n plus 1. So you have n plus 1, n plus 1, and n plus 1. And you have -2 to the n x plus 1 to the n over square root of n plus 3. Okay, so it's going to be like this. And you put absolute value. Okay, and so you're gonna just have limit n go to infinity, and you have 2. Okay, so you see that you can get rid of this guy and this guy, so you have 2 because you have inside absolute value. Okay, so -2 turn out to be just 2, and you have on the bottom guy flip to the top guy, so it's gonna be let's use other color, square root n plus 3 over square root n plus 4. Okay, so you flip it up, and you're gonna have another term which is x plus 1 inside absolute value. And when you have n go to infinity, this one will become the coefficient 1 and 1. So it's turned out to be equal to 1 for the limit. So this limit turned out to be equal to 1. Okay, so this limit turned out to be equal to 1. Or if you confuse, so you can just have n plus 3 over n plus 4. Okay, and this limit is going to be root of 1 for sure. Okay, so that's why I say 1, okay, for all of them. And then you have this limit equal to absolute value of x plus 1. Okay, so you have to absolute value of x plus 1, and this guy will be less than or equal to 1, okay, for conversion. Okay, so for conversion, you have this guy is less than or equal to 1. So in this case, you have, okay, absolute value less than, sorry, I'm not saying less than or equal to, it must be less than 1. And you have absolute value of x plus 1 less than 1/2. Okay, so this one will give you the radius of conversion r. Okay, so this one will be your r. Okay, so that is going to give you the radius of conversion, and the picture for the interval of conversion will be just the center at -1. Okay, so you have the center a equal to -1. Okay, and you have the radius equal to 1/2 from the left and from the right. So it's going to be 1/2 both sides like this. So you would get -1 plus 1/2. So it's going to be -1/2. And you have on the other side, you have -1 minus 1/2. So it's going to be -3/2. So this one will be the boundary. Okay, so this one is going to be your boundary, and you're going to have the conversion lies inside, and you're going to have the diversion lie outside. Okay, so the conversion and this one will be diversion. Okay, so the big picture is look like this one. So we're gonna have the boundary. Okay, so you have two boundary in this case. Okay, so you have two boundaries in this case, and we're gonna have to test them separately. Okay, so you're gonna begin by, okay, so you have x equal to, you have x equal to negative 3 half. Okay, so you have x equal to negative 3 half. You plug x equal to negative 3 half into your beginning series. So it's going to be series n equal to 0. Okay, so it's going to be series n equal to 0 to infinity, negative 2 to the n. And you have negative 3 half plus 1 to the n over, okay, over what is called square root x n plus 3. Okay, so this is what you have here, and then you're gonna just simplify this one. So you have series n equal to 0 to infinity, negative 2 to the n, and you have negative 3 half, so it's going to be negative 1 half to the n over square root n plus 3. Okay, so for this one, it is series n equal to 0 to infinity of 1 over square root n plus 3. And you can test for conversion or diversion for this one. So this one is look like, okay, so I'm gonna say that this one look like 1 over root n. Okay, so this one will be the series that look like 1 over root n. So let's compare. So you have n plus 3 more than n, okay, for sure. So you get root n plus 3 must be more than root n, and you have 1 over root n plus 3 less than 1 over root n. Okay, so you have 1 over root 3 and less than 1 over root n, and you see that this guy diversion. Okay, so this guy diversion, this guy inconclusive. So this guy is divergent. So this one turned out to be bigger, and you not be able to compare this guy. Okay, so you not be able to compare this guy with this guy because this one is bigger, turn out to be divergent. So the smaller one is inconclusive in this case. However, okay, however, it's not going to be far from 1 over root n. So you're going to try to use limit comparison. Try to use limit comparison test. You're going to find limit n go to infinity of 1 over root n plus 3, 1 over root n for bn, okay? And you see that this one will be limit n go to infinity of root n over root n plus 3, and this limit quite easy, so it's going to be n over n plus 3. And so it's going to be limit equal to 1. When you have limit equal to 1, you are using limit comparison. Okay, you not use the ratio test. Okay, one thing that most students confuse is going to be, hey, limit equal to 1 is inconclusive. but this guy is limit comparison. Okay, this one is limit comparison. So when you have limit equal to 1, you'll be able to conclude that the series turned out to be convergent or divergent depending on your Bn. Okay, so this one we're gonna just say this guy is more than 0, and the series n equal to 1 to infinity of 1 over root n you have is divergent with p equal to 1/2, okay, smaller than 1. So we have the series n equal to 1 to infinity of 1 over root n plus 3 is divergent. Okay, so that is gonna be just the way that we conclude that it's turned out to be divergent at that point. Okay, so this one is gonna be divergent at 1/2. Okay, so divergent. So sorry, it's not here. It's divergent at negative 3/2. So for x equal to negative 1/2, okay, so for x equal to negative 1/2, you're gonna have the series n equal to 0 to infinity of negative 2 to the n, and you have negative 1/2 plus 1 to the n over square root n plus 3, and this one will be series n equal to 0 to infinity of negative 2 to the n, and you have negative, not negative, so it's going to be 1 over 2 to the n. Okay, so it's going to be 1/2 to the n over square root n plus 3. And you see that you cancel this guy and this guy. The thing that you have left will be series n equal to 1 to infinity. You have negative 1 inside, and this one raised to the n over square root n plus 3. Okay, so it's going to be square root n plus 3. So it's turned out to be the series that gonna be alternating series. So it's gonna be AST. Okay, so you use AST. So you use the alternating series test. So you're gonna have Bn. Okay, so here you have the sequence. So you consider the sequence 1 over root n plus 3, and you need to show limit equal to 0 and decreasing. Okay, and the conclusion will be conversion by AST. Okay, so if you be able to show them, the conclusion turn out to be conversion by AST, and you're gonna have the conversion here. So it's turned out to be diversion at the negative 3 over 2, and it's going to be conversion at negative 1 over 2. So it's going to be the interval of conversion turn out to be, so interval of conversion, you have the point negative 3 over 2, you have the point negative 1/2, you have negative 1 in the middle, you have R equal to 1/2. Okay, so you have R equal to 1/2, and you're gonna have conversion, you have diversion, you have conversion. So the interval turn out to be in the form of, so it's gonna turn out to be here. Okay, sorry, it's gonna be here that you exclude. Okay, so exclude. and you're gonna include this guy. Okay, so it's gonna be, you're gonna include this guy. Okay, and it's gonna turn out to be conversion inside this interval. Okay, so it's gonna be conversion inside this interval, and it's gonna be diversion outside. Okay, so this is how we give the conclusion for this power series. Okay, so I will let you do number 3 on your own first to see what you understand. Okay, so this one, I'm gonna let you do this one on your own. Okay, for this limit equal to 0 and decreasing. Okay, please show by just computing the limit equal to 0 and you show decreasing, you'll be able to conclude. Okay, so you do this on your own, and you do number 3 on your own. Okay, so you do number 3 on your own to check whether you understand the thing that we are doing so far, and this one will be given the solution during the recitation. Okay, so this one is going to be conversion and diversion where or something, so that what we're going to learn is not going to be that difficult to do. Okay, so for this one, we're gonna do this one during the recitation. The next one, okay, so the next one will be about the representation of function as power series. Okay, so we're gonna talk about the representation of function as power series. We know that, okay, we have the series n equal to 0 to infinity of u to the n equal to 1 plus u square plus u cube, go on. And is this guy equal to 1 over 1 minus u if absolute value of u less than 1. Okay, so this is one formula for geometric series. Okay, so this one is coming from the geometric series. Okay, so this one is the geometric series. Okay, so it's going to be geometric series. And the way that we be able to apply this one will be, you need to be able to identify u. So you see that if you have the function 1 over 1 plus x squared, the 1 plus the plus x squared can be written as, okay, so let me just highlight, the plus x squared can be written as negative, okay, of negative x squared, and this will play the role of u. Okay, so you have u. Okay, so you have u equal to negative x squared, and this one will be u. Okay, so this one will be u. And so you'll be able to represent this function. You'll be able to represent this function in terms of power series. Okay, so this one we're gonna call power series representation. Power series representation. Okay, so this one is called power series representation. And this one will be just the series n equal to 0 to infinity of negative. Okay, so negative 1 to the n and x to the 2n. Okay, so that is the power series representation. And this one only valid for, okay, so this one only valid for absolute value of x squared. Absolute value of negative x squared smaller than 1. Okay, so you have absolute value of u. Okay, so u is negative x squared. So you have absolute value of x squared less than 1. So this one, if you solve, you have x squared smaller than 1. So you get absolute value of x smaller than 1 by taking of the square root both sides. Okay, so this one, you must keep this one also in mind. Okay, that is not going to be valid for any x. It's going to be the valid only the one that going to be absolute value smaller than 1. Okay. For the next one, you have x squared over 2 minus x. So you'll be able to write this one. So you pull out x squared on top, you pull out 2, okay, from the bottom. So this thing will be 1 over 1 minus x over 2. Just pull out 2 from the bottom. And you see that this one gonna be x squared over 2. Okay, it's going to be x squared over 2. And you have this series, okay, this function. So you get u equal to x over 2. Okay, so you get u equal to x over 2. So it's going to be series n equal to 0 to infinity, u to the n, okay? And you have the power series representation x to the n over 2. So it's going to be x to the n times x squared. So it's going to be x to the n plus 2. And you have 2 to the n times 2. So it's going to be 2 to the n plus 1. And this guy is going to be conversion only when you have absolute value of x over 2 smaller than 1. Okay, so it's going to be absolute value of x over 2 smaller than 1. So you would get absolute value of x smaller than 2. Okay, so this is what you have so far. So the thing that we can do to power series and function, beside the first thing that I asked you or I teach you already, is gonna be you be able to differentiate the power series and you be able to integrate the power series term by term. Okay, so you be able to differentiate f, you be able to integrate f accordingly, and you would get something like the term by term differentiation or term by term integration. Okay, so this is going to be look like you differentiate inside the power series, or you be able to integrate the power series. So when you differentiate, you see that dip c0 disappear. When you dip x minus a, it's going to be, so it's going to be the series C and C plus C0 x minus, so it's going to be this guy and this guy and this guy. Okay, so you must have something like this. Okay, so it's going to be C1, C2, C3, and so on. And it's going to be NCN and x minus a to the n minus 1. How would this formula come from? So you see that when you differentiate this guy, n gonna come down and you're gonna reduce the power by negative 1. So it's gonna be NCN x minus a to the n minus 1. Okay, so this one will be just differentiate term by term. And for this one, you can integrate. When you integrate, it's gonna be integrate C0, you get when you integrate this one, it's going to be what? It's going to be Cn x minus a to the n plus 1 over n plus 1 like this. And you have to plus constant, okay? And this c come from that plus constant. And it's going to be you integrate this guy term by term. Okay, so this is what we can do also. Okay. So we're gonna find a power series, okay, representation for the given function here. So you see that this one is not the thing that we have, okay? So this is not the thing that you have here. It's gonna be, it's not gonna be in terms of 1 over 1 minus u, but it look like you have 1 minus u, but it's gonna be, you have square. Okay, how would we have the power series that will represent this one? So you see that you gonna begin with, we begin with 1 over 1 minus x. Okay, so it's going to be 1 over 1 minus x, and this guy will be 1 plus x squared plus blah blah blah, and this one will be series n equal to 0 to infinity of x to the n. Okay, and you have absolute value of x smaller than 1. Okay, so this one look like this one, and you're gonna differentiate. Okay, so you see that in order to have square here, you not be able to just raise square both sides, because when you raise square both sides, this one will be horrible. Okay, so this one you're gonna get many terms, so it's not quite good to do that. So for this one, the thing that we be able to do is gonna be, we're gonna differentiate both sides. Okay, so we differentiate both sides. So you see that you get 1 over u, so it's going to be negative 1 minus x squared. And you have to multiply negative 1. This one is differentiate the inside. And you have the series n equal to 0 to infinity. And you differentiate x to the n, so it's going to be n x to the n minus 1. Okay, and you see that this one is also good. And you also notice that if you have n equal to 0, okay, if you have n equal to 0, this term will turn out to be disappear. Okay, this term will turn out to be disappear because it's going to be 0. So here we're going to move to n equal to 1. Okay, why don't you have n equal to 0? Because if n equal to 0, this term is disappear anyway, so we not waste anything. So it's gonna be we're gonna begin at n equal to 1 instead. Okay, so that's the thing. And you see on the right side, so it's gonna be 1 over 1 minus x square, and this one will be series n equal to 1 to infinity of n x to the n minus 1 when absolute value of x smaller than 1. Okay, and you like to have x on top. Okay, so you like to have x on top, so you're gonna multiply the whole thing by x. Okay, so you're gonna multiply the whole thing by x, both sides. So when you multiply everything by x, you reach the final answer. Minus x squared equal to series n equal to 1 to infinity n x to the n, and you have absolute value of x smaller than 1. Okay, so this is gonna be just the way to obtain the power series representation for this one. Okay, so this one will be the final answer for this power, this function. The next one I let you do on your own, but I will tell you that we will begin with, okay, so you see the structure, you should begin with 1 over 1 plus 3x, okay, and you're gonna have the series n equal to 0 to infinity of what? Okay, so that is gonna be the thing that you have to work out, and you may just follow the number 1, so you be just able to differentiate both sides or something. Okay, so be careful on differentiate the inside a little bit, and you should get the correct answer. For number 3, hey, it's turned out to be log. How could we deal with log? Okay, the thing that we can deal with log is going to be, we must know that, okay? So we begin with just 1 over 1 plus x, okay? And 1 over 1 plus x turn out to be 1 over 1 minus x. And this guy becomes series n equal to 0 to infinity of negative x to the n. Okay, so it's going to be negative x to the n. And you're gonna integrate both sides. Okay, and you're gonna integrate both sides. So you integrate 1 over 1 plus x, so this one will be just u equal to 1 plus x, and you have du equal to dx. So this guy will become integrate 1 over u du equal to log absolute u. Okay, so it's going to be the thing that we are looking for. So it's going to be log absolute 1 plus x. Okay, so this one will be just the thing that you have. Okay, and you have only for x. Okay, so this one is valid only for absolute negative x smaller than 1. Okay, so you have absolute value of negative x smaller than 1. So this one is going to be x going to be absolute value of x less than 1. So you have x between negative 1 and 1. Okay. And when you have x negative 1 and 1, you have 1 plus x will be more than 0. Okay, so you have 0 more than x plus 1 less than 2. So this one become, so this one, this term, you see, this term lie between 0 and 2. So this term turned out to be positive. So you can erase the absolute value. Okay, so you can just erase the absolute value and you can just put parentheses. Okay, so you have something that extra for a little bit that, okay, why don't we have absolute value? Because you know that 1 plus x is positive, so you can ignore the absolute value. And you see on the other side that you're gonna integrate this guy. Okay, before we integrate this guy, let me write them in terms of series n equal to 0 to infinity. And this one will be negative 1 to the n, and you just integrate x to the n dx. Okay, so you're gonna just integrate, oh, I forgot dx. When you integrate, you must have your dx. And you see that this integral become c plus series n equal to 0 to infinity, negative 1 to the n, and you have x to the n plus 1 over n plus 1. Okay, so this is the blue guy. Okay, so this is the blue guy, this integral. Okay, so this integral turned out to be x to the n plus 1 over n plus 1, and you have log absolute log 1 plus x on the other side. Okay, so we're gonna find c by putting x equal to 0 both sides. Okay, so you're gonna find c by putting x equal to 0 both sides. When you plug in x equal to 0 for the left side, it's gonna be log 1. Okay, so it's gonna be log 1, and on the right side, it's gonna be c. Okay, let me use the red color. And when you plug in x equal to 0, this guy will become equal to 0. okay, because it's 0 to the n plus 1. So it's going to be plus 0. Okay, so you would have c equal to log 1. So this one will give you c equal to 0. Okay, so when you have c equal to 0, this will lead you to log 1 plus x equal to series n equal to 0 to infinity, negative 1 to the n, okay, x to the n plus 1 over n plus 1. Okay, so this one will be just this series, and this one is valid for absolute value of x smaller than 1. Okay, so this one is how we do this example. So it's gonna turn out to be able to represent the given function in terms of power series. The last one is about arctan. Okay, the last one is about arctan, and you see that, hey, it's not gonna be only the thing that we used to have, right? However, if you recall, the arctan one is the formula for integral of 1 over 1 plus x squared dx. Okay, so arctan x will be just the integral of 1 over 1 plus x squared dx. And so we begin with, okay, so we begin with 1 over 1 plus x squared. Okay, again, this one is 1 over 1 minus x squared. And it will become series n equal to 0 to infinity, negative x squared to the n. Okay, so, and you're gonna integrate this guy both sides. Okay, I will first let you do this one, and I'm gonna give you the solution during the recitation. So this one is square smaller than 1. Okay. So that would be all of the thing for this clip. Okay, so in this clip, we learned so far how to find the radius of conversion, and we learned how to determine the interval of conversion. Sometimes it's turned out to be closed interval, and sometimes it's turned out to be half closed, half open interval. And I'll let you do this one on your own from the beginning. And you have the way that we be able to representation, or that we can represent the function in terms of power series. When you have function, you be able to represent them as power series by beginning with the geometric series in some term. Okay, so I let you do this 2 and 3 on your own. Next time, we're gonna turn out to study about the Taylor and the Maclaurin series, which gonna be, I would say it's gonna be fun. However, it's gonna be also confusing, okay, in the way that we're gonna do. Okay, so see you in the next clip.